So now we want to talk about an operation that we can do on our vector space. And that operation is actually called an inner product. Now, what the inner product is, it takes in two vectors from our n-dimensional vector space, and it's going to turn around and return us a scalar real number. And we're actually kind of familiar with this from a vector operation from Calc 3, where we just take two vectors. So if we have a vector v, that looks like v1, v2, all the way up to v sub n. And we've got another vector w, which looks like w sub 1, w sub 2, all the way up to w sub n. Then our inner product is actually just the component-wise multiplication. So it's our v1 times w1 plus our v2 w2 plus our v3 w3 all the way up to our v sub n wn. Now, we probably recognize this as being just our usual dot product from our third semester calculus. And we've really just kind of taken that original function and generalized it to really be the same thing in higher dimensions. So one thing that we have for these dot products, and yes, we're using kind of interchangeable names for them. Sometimes you see them referred to as dot products, other times you see them referred to as inner products. That the familiar notation that we have is just using them as a dot in the middle, but alternative notation, we kind of have these angle brackets for them with a vertical bar in between, and so we might write them as an expression that looks like this. So throughout any of our discussion, we'll just use these as kind of interchangeable notations for dot products or inner products. Now what we want to do is to remember some of our familiar properties that we had, and back from Calc 3, we had with our dot products. And so probably the first one to remember is that if we had our vector, say v1, v2, all the way up to v sub n in component form, that we had the length of v as really just being the square root of the sum of the squares of its individual components. So all the way up to v sub n squared. And so remember that we can write this as actually being just the square root of the vector v taken with the square root of the dot product with v taken with itself. And if we really wanted to take this a step further, we could really define a distance between two vectors, say v and w, as really just being the length of v minus w. And so that ends up being just our square root of v minus w inner product with v minus w. And so we have our first property of our inner products. Really that being for any vector v in our n-dimensional real vector space, that we have the inner product of v with itself is always going to be greater than or equal to 0. And we also know that if the inner product of v with itself is equal to 0, then the only time that that's going to happen is when v itself is going to be the 0 vector. So let's take a look to see why this might be true. Well, our definition of the inner product is really just the sum of the squares of our components. And so since we know that v sub I squared is going to be greater than or equal to 0 for all I, if we add those together, then it naturally follows that the sum of the squares is going to be greater than or equal to 0. And so kind of that first property we get immediately, that the inner product of v with itself is going to be greater than or equal to 0. In particular, we noticed that for the 0 vector, which is just going to be all zeros, that if we do the inner product of the 0 vector with itself, sure enough, we get a bunch of 0 squareds all the way up to n of them added together, sure enough, gives us 0. And so we have, kind of almost trivially, that the 0 vector inner product with itself is going to equal 0. Now let's see if we can get the other half of the implication. So if we suppose that we have a vector v, and we take the inner product of v with itself, and we get 0, then this means that the sum of our squares is really going to be 0. So now, from our properties of real numbers, we know that if there existed a j such that v sub j was going to be greater than 0, then we know that v sub j squared is going to be greater than 0. And so when we add all of those together, that would mean that the sum over all of those from 1 up to n of my v sub I squared is going to be strictly greater than 0. Now, that would otherwise give us a contradiction with assuming that the thing was 0. And so what we then have tells us that v sub I squared is going to be 0 for all I. But then again, following from our real numbers, v sub I squared is going to be 0 if and only if each one of our factors is 0, and so in particular for v sub I to be 0. So thus we conclude that v is going to be the 0 vector. And so we have our first property of the inner products proven. So our second property of our inner products is really kind of almost immediate, and that being symmetry. That if we take any two vectors, so if we've got a vector u and we've got a vector v in our n-dimensional vector space, then the inner product of u with v is going to be equal to the inner product of v with u. And that is pretty much immediate from the definition. So if we do u inner product with v, that's going to give us the sum, I goes from 1 to n, of u sub I times v sub I, but then that's exactly the same thing. I goes from 1 to n as v sub I times u sub I, and that's the same thing that we get from our definition of v inner product with u. For our third property, again, this one pretty much follows from our properties of real numbers and some algebraic manipulation. So for any vectors that we have, now we have u, v, and w in our vector space r to the n. Then if we do the inner product of u plus v with w, that inner product distributes across the sum. So we have u inner product with w plus v inner product with w. Now the proof for that one, again, really isn't too bad. If we start off with u plus v inner product with W is just going to be the sum, I goes from 1 to n, of the component-wise product. So the component of the ith component of u plus v times the ith component of w. Well, now our ith component of u and v is really just going to be u sub I plus v sub I. And so we have that times our w sub I. So where does that come from? That's from our properties of, or really from our definition, vector addition. So now we can apply just our properties of real numbers, and we can distribute that w sub I. And so what that gives us is just the sum from 1 to n of our u sub I w sub I plus our v sub I w sub I. Well, of course, we can separate those out just with our properties of addition, so that really just becomes our sum, I goes from 1 to n, of our u sub I times w sub I plus our sum, I goes from 1 to n, of our v sub I times w sub I. And then kind of bringing that back to our definitions of our inner products, that is our inner product of u with w, and our second sum is just our inner product of v with w. So now really this, coupled with our symmetry property, really gives us distribution in both components. And so what we really then have is that u plus v inner product with w gives u inner product with w plus v inner product with w, and that symmetry goes the other way as well. If we have u inner product with v plus w, then that gives us u inner product with v plus our u inner product with w. So now we need some kind of property that happens to deal with scalars. And so we have property 4. Then if we've got some real number c, and if we take a couple of vectors, say u and v in our n-dimensional real vector space, then we have this property that if we do c times our vector v, and we inner product that with w, that gives us the exact same value as if we did v inner product with c times u, and we can actually pull that c to the outside so that we get the exact same value as if we did the inner product of v with u and then multiplied by c. So let's see how this works. Well, if we have our inner product of cv with u, what is that going to be? Well, it's going to be our sum, I goes from 1 up to n, of the ith component of c times v times the ith component of u. Now, kind of our definition of scalar multiplication, what is that ith component of c times v? Well, it's going to be c times vi. And so that really just follows from our definition of scalar multiplication. And so what happens from here? Well, now c, v sub I, and u sub I are all just kind of scalars, and so they're just real numbers. And so we've got our usual old associativity properties and commutativity properties with our multiplication. So we can say that that is going to be the same as the sum, I goes from 1 to n, of v sub I times c u sub I, which, again, kind of reversing everything, is going to be our inner product of v with c times u. And then what we could also do is to take that C and we could use our distributive property of real numbers and factor that C out, so that if we had, this was going to be I up to n, factor that C out, and I'm just multiplying V sub I and U sub I at that point. We use our distributive property, factor that C out of each and every term. So V sub I, U sub I, and we end up with C times our inner product of V with U. And so with that property, we know exactly how our inner products interact with scalar multiplication. So kind of putting this all back together, that we have our following properties of inner products. So for our vectors, say u, v, and w in r to the n, and for any old scalar c that we have, number one, that the inner product of a vector with itself was greater than or equal to 0, and we had the equivalent thing that if the inner product was going to be 0 if and only if v was going to be the 0 vector. Our second was that our inner products were going to be symmetric. So the inner product of v with u gave us the same value as the inner product of u with v. Then we had our distributive properties, which said that if we did the inner product of u with the sum of v and w, that it just distributed across. So we have the inner product of u with v added to the inner product of u with w. And then finally, how did things work with our scalars? That if we did the inner product of the scalar times c and v with the vector u, we could actually move that constant to the other side and first multiply by u, or we could just factor that constant out, and so we get c times the inner product with u and v. So kind of another property that we have that is going to be important when we're actually talking about our distance formula with the distance between these vectors is a theorem that's popular enough to have its own name, that it's the Koshi-Swartz inequality. And basically what it says is that for any vectors, so we've got a vector u and a vector v in r to the n, then the absolute value of the inner product of u and v is going to be less than or equal to the magnitude of u times the magnitude of v. So how we go about getting this inequality is really a nice example of applying some of the properties that we've seen. What we want to do is to choose some scalar c that could be anything, and we're going to take our two vectors u and v in our real vector space. Now what we're going to look at is the inner product of c times v minus u with itself. So c times v minus u. Now from our properties before, we know that the inner product of a vector with itself is going to be greater than or equal to 0. So now applying those distributive properties and our properties of scalars, we can kind of pull all of our c's out, distribute, and let's see what happens. So now distributing our first vector across the other two vectors, we get something that looks like c times v minus u, inner product with our first vector, c times v, plus the inner product of cv minus u with our vector minus u. So now this constant c, we can actually pull that one to the outside. And we can do the same thing with this negative. We can pull that one to the outside. So we get something that looks like c times cv minus u, inner product with v, minus a cv minus u, inner product with u. So now we distribute again. And so we have c times our inner product of cv with v, and kind of doing the same thing, minus the inner product of u with v. Now if we do the distribution again, what do we have? We distribute our u so that we've got a c times v, inner product with u, minus a u, inner product with u. So if we then pull out our c's again and distribute everything, we ended up with an expression that looks something like c squared times v inner product with v minus c times u inner product with v minus c times v inner product with u plus, when we distribute that negative, a u inner product with u. So now we can use the symmetry on our u inner product with v and v inner product with u. And we can take our v inner product with v and we can write that as the length of v squared minus 2 times our c times the inner product of u with v. And then finally, the inner product of u with itself becomes the magnitude of u squared. Now, where we were going with this was that we took the inner product of a vector with itself, and we so knew that this was always going to be greater than or equal to 0. So that all of this really just becomes a quadratic in our variable c. And so what that means is basically it being always greater than or equal to 0, we've got one of two pictures. Either our quadratic is doing something like this, or our quadratic is doing something like this. And so what that tells us is that our quadratic either has 1 0 or it has no zeros. If it has no zeros, then that means that your discriminant is going to be negative. If it has only 1 0, then it means that your discriminant is going to be equal to 0. And so what we conclude is that the discriminant of this quadratic must be, so our discriminant, which is going to be our b squared minus 4ac, so that's going to be our negative 2 times our inner product of u with v squared minus 4 times a, which is our length of v squared, times c, our length of u squared, is going to be less than or equal to 0. And so what we have is an expression that looks something like 4 times the inner product of u with v squared minus 4 times our length of u squared times our length of v squared is going to be less than or equal to 0. Well, kind of rearranging everything, dividing by 4, we end up with the inner product of u with v squared is going to be less than or equal to the length of u squared times the length of v squared. Or taking the square roots of everything, we have minus the length of u times the length of v is going to be less than or equal to the inner product of u with v, is going to be less than or equal to the length of u times the length of v. Or, kind of said more concisely, that the absolute value of u with v is going to be less than or equal to the length of u times the length of v. And so we have our Cauchy-Swartz inequality. We can then use our Cauchy-Swartz inequality in the proof of something called the Triangle Inequality, which says that for any u and v in our n-dimensional vector space, that the length of u plus v is going to be less than or equal to the length of u plus the length of v. So let's take a look and see how that proof might go. Now we have that the length of u plus v squared is going to be equal to our inner product of u plus v with itself. Now, using the distributive properties of our inner product, we can write this as the inner product of u with u plus the inner product of u with v plus the inner product of v with u plus the inner product of v with v. And then, kind of by the symmetry of things, we can replace our v plus u and u plus v. Those can go together so that we've got something that looks like the length of u squared plus 2 times the inner product of u with v plus the length of v squared. Now we apply our Cauchy-Swartz inequality to then tell us that this is going to be less than or equal to the length of u squared plus 2 times the length of u times the length of v plus the length of v squared, which this is just our algebraic expression for the square of the length of the sum of u and v. And so, kind of putting this together, what we really have is that the length of u plus v squared is going to be less than or equal to the square of the sums of the lengths of u and v. And since everything is non-negative, we can just take the square roots of everything. Our inequalities stay the same direction, and so what we have is just that the length of u plus v is going to be less than or equal to our length of u plus our length of v. And that gets us the conclusion that we wanted. And so now, to kind of bring this back to the distances that we were talking about earlier in the video, kind of 3 properties that we want for distances, and this is true not just in linear algebra but also in other areas of mathematics. 3 properties that we want the distance between 2 objects to be greater than or equal to 0, and we want the distance between those 2 objects to be 0 if and only if that the 2 objects are going to be equal. So we want our objects to be separated by some positive difference if they are distinct objects. The second thing that we need is that the distance between those 2 objects doesn't really matter whether you're going from u to v or you're going from v to u. We want those distances to be the same. And then finally, a third property is basically kind of has to do with this picture. If we've got one object over here at u, another object over here at v, and if we decide to go anywhere else in between. So if we look at the distance between u and v, but if we make a stop somewhere else, that we really get that the distance between u and v should be less than or equal to the sum of the distances if we make any other stop anywhere else other than u and v. Then it really forms something like a triangle, and so we actually call this the triangle inequality. And so, in particular, for our vector space, we can define the distance between our vectors to really just be the length of the difference of u minus v. And so that's just going to be the square root of our inner product of u minus v with itself. And so our first property of our distance formula, namely that d of u and v is going to be greater than or equal to 0, and the fact that d of u v being 0 happens only when u is equal to v. Well, this property follows, again, from our properties of our inner products, so that it's pretty easy to see. For our second property, that we have symmetry between our distances, again, that's pretty easy to see from our scalar properties of our inner product, then implies that condition. And finally, for our triangle inequality, we have that the distance between u and v can be represented as, so it's the difference of u and v, but then we can play this common math trick where we subtract something and add something so that everything stays balanced. Now, from our triangle inequality, this is going to be less than or equal to, if I group the first two terms together, I get a u minus w. I group the last two terms together, I get a w minus v. And this is exactly what I mean when I say that this is the distance between u and w, and the distance between w and v. And so our triangle inequality from the previous theorem just applies to the triangle inequality to get our distance formula. And so we have actually something that does give a distance on our vector spaces. And so the last thing that we really need to talk about is maybe one interpretation of what the inner product actually gives us. And so for that, we again kind of come back to our arrow representation for our vectors, so that one vector is going to be v, another vector is going to be u, and then the other vector that we have out here is going to be v minus u. And if we just look at the magnitude of all of those sides, so now we're really looking at it as a triangle, then we have this angle in between our vectors theta. And so what happens there is really from our law of cosines back in trigonometry, that the length of v minus u squared is going to be equal to the length of u squared plus the length of v squared minus 2 times the length of u times the length of v times the cosine of the angle in between u and v. And so what happens there? Well, we come back to what's our value of the square of u minus v. Well, I can write that as an inner product of v minus u with itself, and then use my distributive properties of my inner product to rewrite this as the inner product of v with itself minus the inner product of v with u minus the inner product of u with v, and then plus the inner product of u with itself. And so that gives us, again, an expression that looks like the length of v squared minus 2, using our symmetry relations, the inner product of u with v, and then the length of v squared. And so what we have an expression that basically looks like this. So we have something that looks like the length of u squared plus the length of v squared minus 2 times the inner product of u with v is going to be equal to the length of u squared plus the length of v squared minus 2 times the product of the lengths times the cosine of the angle in between. Well, of course, what do? We cancel terms left to right, so our lengths of u and v cancels out. We cancel our values of the negative 2's, and so we're just left with something that looks like the inner product of u with v is going to be the length of u times the length of v times the cosine of the angle in between. And so this really gives us an interpretation for what the inner product is really telling you. But then it also gives us a means of saying, well, what is the angle in between those two vectors? We have a computational way of finding that easily. It's just the length of u inner product with v divided by the length of u times the length of v. And so even in more abstract situations that we'll talk about later on, we can still talk about angles between algebraic objects that maybe we wouldn't think of as having angles between them. But more about that later in an upcoming video. See you guys then.